this is a data frame with 150 observations and 5 variables. First 4 variables are numeric, and species is a factor variable which has 3 different levels. So we'll make scatter plots with first 4 variables which are numeric. So gap between the scatter plots I'm keeping 0, and I also want to give colors to the dots represented by 3 different species. So let's have 3 different colors: red, green and blue. And then we also specify iris $sign species, and the symbols I'm using 21. So let's run this. So for each of the numeric variables we have histograms, and we also have scatter plots for each combination. So this is sepal length versus sepal width. We have this scatter plot. In the upper triangle we have correlation coefficients. So we also see in these scatter plots that 4 variables really help in some way to separate 3 different species. So we can see red, green and blue separated out in some cases, but in some cases there is some overlap too. So we want to carry out a discriminant analysis that will help to find linear combination of these 4 variables that will give us the best possible separation among these 3 groups or 3 different species. But before we do that, let's do data partitioning. So we use a random seed, in this case 555, so that training data set and testing data set that I get randomly, so you also get exactly same if you use 555. If you are going to use another random seed, then the training data that I get may not be exactly same as yours. So sampling with replacement is true, and let's go for 60% for training and remaining 40% data set for testing. I and E equals, so for equal we use 2 equal signs, equals 1, comma. So you can see training has 86 observations, and for testing we are going to have 64. So for this we'll use library called MASS. We'll make use of function called LDA for linear discriminant analysis, and our model is species as a function of all other 4 variables, so I'm putting dot, and our data is training. And let's save this because this is linear discriminant analysis, so I'm just going to use this name linear. So if you want to look at the output, you can run this line linear. So it starts with the model, and then it has calculated prior probabilities of the groups. So in the training data set, 38.3% belong to this first species, 31.3% belong to the second species, and about 30% belong to third species. And then we have group means. So for each species and each variable we have the averages. Here we have coefficients of linear discriminants for LD1, so that's the first one, and this is LD2, second one, for each of the 4 variables. And then we have proportion of trace. So we can say the percentage separation that is achieved by the first discriminant function is 99.37%. So that's very high, almost close to 100%. Whereas percentage separation, which is achieved by the second discriminant function here, is quite small. It is only 0.63%. If you want to look at what other output you can get, you can say attributes linear. For example, if you want to see the first one, so you can say linear $sign and prior. So you get these percentages that we have for each species in the training data. Similarly, if you want to look at linear $sign counts, so how many data points for each species in the training data? We have 33 for the first one, 27 for the second, and 26 for the third one. Similarly, if you go for the scaling, then you have these values of the coefficients. So let's look at the predictive performance by making some histograms. And our model is linear. We'll use training data. Let's store this in P. So once you run this, predictions are available in P. If you run P, we get a lot of output here. So for each data point in the training data set, what is the prediction is given here. So you can see, so this is 31, 32, 33. So for first 33 data points, the prediction is that they belong to Setosa species. Similarly, for next few, we have prediction for the second species and then third species. It also gives output for the probabilities. So in fact, if you look at the first observation in the training data, probability that it belongs to first species is almost 1, very close to 1. And the probability that it belongs to second species is very, very small, 1.5 times 10 to the power of negative 21. So it's almost 0. Similarly, the probability that the first one belongs to third species is 3.7 times 10 to the power of negative 40. So even smaller than this. So almost 0 here. So that's how this one is predicted to be in the first species. So we have probabilities followed by score for each observation in the training data set. So these are calculated using the coefficient that we had seen earlier. So it uses data points from the first 4 variables, and using the coefficient, it calculates this score here. So this is done for all the data points in the training data. So using this, we can make a histogram LDA-HIST, where data equals our predictions, and within predictions we have this X, where we have these values that we see, and the first histogram will make for LD1. So let me put comma 1, and we can say G equals training $sign species. So this is what we get. So these histograms are based on LD1, this column here, and you'll notice that separation between first histogram for the first species and the second histogram, which is for the second species, is quite good. So there is no overlap. Similarly, separation for first species and the third species also is quite good. So there is no overlap, but there is some amount of overlap between second species and the third species. So if you look at the trace value that we had seen earlier, so the percentage separation achieved by the first discriminant function is like 99.37%. So that's why we have so clear separation among the 3 species. But if you do the same thing for LD2, where this separation percentage is quite low, less than 1%, so we may see lot of overlap between the 3 histograms. So let's do this. So this time we are plotting the second column. So you can see there is a lot of overlap among the 3 species. So the separation achieved by LD2 is not that great. So for biplot, we'll use library dev tools. We also need to install from GitHub a package called ggord, and we need to make use of fawda123/ggord. So since I have already installed this, I'm not going to run this, so I'm going to convert this into a comment. So make sure to install this package before running this library line. So we can now use this for making the biplot. So our linear discriminant model is in linear, and we want to plot training $species. So this is the plot we get. In fact, if you want to spread this out just like the x-axis, which is from -10 to 10, so we can make that adjustment here by saying y limit equals -10 and 10. So this is the plot we get. So on the x-axis we have LD1, first discriminant function, which helps to achieve 99.37% separation, and on y-axis we have second discriminant function, which helps to achieve only 0.63% separation. So you can see that the three species are separated quite well. In fact, the first species data points are quite far away from second and third, but there is some amount of overlap between second and third species, as you can see from green and blue. So for any new data point, if we calculate the linear discriminant score, and if the value is somewhat above 5, so that means we can classify that as first species. However, if the score is between 0 and somewhere, let's say -3, then it should belong to second category or species. And if the score is less than -5, then definitely it belongs to third species. And LD2, you can see, doesn't help to get that kind of clear separation. We also have 4 variables indicated on this biplot. So if you look at the output again, so if you look at the coefficients of LD1, you can see sepal length and sepal width are both positive. So you can see sepal length and sepal width, so they are above this 0. So they are in the positive direction. So you can see the coefficient is 1.25 for sepal length. So you can see it is somewhere here, 1.25. Similarly, petal length and petal width are on the negative side. So you can see these arrows go to the left of 0. Petal length is -2.6. So this is somewhere here. And petal width is -2.1. So this is somewhere here. If you look at LD2, sepal length and petal width are negative. So these two are below this 0 line, and the other two have positive coefficients. So you can see they are above the 0 line. So this is a very informative graph about the model that we have here. For the partition plot, we'll use library called KLA and capital R. So you may have to install this in case you have not installed this earlier. So we have species as a function of all other variables, and our data is training, and the method that we are using is LDA for linear discriminant analysis. So we run this line. So it gives us classification of each and every observation in the training data set based on our linear discriminant analysis model for every combination of two variables. So we have sepal length versus sepal width, sepal length versus petal width, and so on. So we have 6 plots. So you can see here data points for the first species, Setosa. So this is quite far away from other two, and between second and third species there is some amount of overlap, and more or less it repeats in every plot. So note that we have developed a linear discriminant analysis model. But you can also develop quadratic discriminant analysis model and do this plot very easily. So for method, instead of LDA, if you say QDA for quadratic discriminant analysis and then run this, so you can see these lines, you'll find it, they are slightly different compared to what we had for linear discriminant analysis. So let's store predictions in P1 for developing confusion matrix. So we'll use our linear model that we developed, and our data is in training. And also to get the class values, I'm putting a $ outside the parenthesis, and we can say class. And then we create a table with the predictions versus actual values. So we can say predicted, which is our P1, and actual is in training $species. And let's store this in TAB. And then when you run tab, you get the confusion matrix. So you can see actually there were 33 observations belonging to first species, and our prediction model also says they should belong to first species. So this is a correct classification. Similarly, 26 belong to second species, were also predicted to be belonging to second species. So there were 26 correct classification for the second species and 25 for the third one. There was one case which was misclassified as second one when it actually belonged to the third category. And another one which was misclassified is here. Actually it belonged to second species, but the model says it should belong to third. So 2 misclassification out of 86. So we can calculate accuracy as sum of diagonal of tab divided by sum of the entire tab. So we are adding 33 plus 26 plus 25 in the numerator and dividing that by the total. So that will give us accuracy of the model. So accuracy is 97.6%. This is based on training data that the model has already seen, but it has not seen the testing data. So let's see how it performs with testing data. So we'll store predictions in P2. So now we have testing, and we just want to extract class. If we look at tab 1, we get this confusion matrix. So there are 17 plus 22 plus 24 correct classifications, and there is one misclassification. So let's calculate accuracy. So using linear discriminant analysis, we were able to classify the 3 species with a high level of accuracy.